For centuries, people have watched tops wobble as they spin on tables. But recently, scientists have had their eyes on the wobble of fundamental particles called muons. Scientists have made incredibly precise calculations of how muons should move. So making an equally precise measurement of this property is a good test of the theoretical model. If theory and experiment don't agree, then there must be undiscovered particles or forces at work. But first, what exactly is a muon?
So a muon can be thought of as a heavier cousin of an electron. It's about 200 times more massive, and it has many of the same properties that an electron has, except that because it's heavier, it can also decay, and in general it takes about 2 microseconds and then it decays into an electron.
Most importantly, muons are electrically charged particles with a property called spin. As a result, they behave as if they have internal magnets.
So a muon has this quantity which effectively means that if you put it in a magnetic field, it spins around just exactly like a spinning top. And the G factor, this G number that we're trying to measure, directly relates the strength of the magnetic field to the spin of the muon and tells you how quickly the muon will spin when it's in that magnetic field. So the G factor causes the muon spin to wobble when you put it inside a magnetic field.
Scientific theories initially predicted that the muon should have a G factor equal to exactly 2. But it wasn't so simple.
So in general, you might think that the vacuum itself, if you just have a vacuum chamber with nothing in it, there's nothing there. But in reality, due to something called the uncertainty principle, we have particles that come in and out of existence for just a blip. And so they come in and then they vanish again, and then they appear and vanish again. And so as our muons are going around, they're not only interacting with the magnetic field, but they're also interacting with these virtual particles, which come in and out of existence.
I like to think of it a bit like when you put too many pieces of paper behind a fridge magnet. If you add an extra one in there, it doesn't feel the force as much and it will fall off your fridge. The muon's going to just slightly, for a tiny amount of time, feel a slightly different amount of force, depending which virtual particle got in the way.
In June of 2020, a collaboration of more than 170 scientists completed an extraordinarily complex set of calculations and arrived at this value for the muon's G factor.
The more precisely we can measure the speed, the more sensitive we are to learning about different types of these virtual particles. And the hope is that eventually, if we measured it really, really precisely, we might be sensitive to new particles from beyond the standard model that no one's measured yet.
That's where Fermilab's Muon G-2 experiment comes in.
The Muon G-2 experiment involves taking muons and we put them inside a big magnet where we store them and send them around and around. And while they're in there, we measure the frequency at which their spin rotates within the magnetic field. So we can measure this quantity very precisely, and it can also be predicted very precisely. And the main goal of the experiment is to make the measurement and compare with the theory. And if they disagree, then it's telling us that there's something in nature which is not in the theory. So the thing in nature is affecting the measured value and making it different from the theory, which doesn't contain this new physics.
In 2013, an enormous 50-foot magnet traveled 3,200 miles by land and sea from Brookhaven National Lab in New York to Fermilab. This magnet is hundreds of times stronger than those magnets on your refrigerator.
So this experiment builds on a previous experiment that ran at Brookhaven National Laboratory around the 2000 mark. It's a very similar experiment, actually using the same magnet to store the muons.
It's a C-shaped magnet, which is 7 meters in radius. And the unique feature of the magnet is how well shimmied it is, how uniform the magnetic field of the magnet is. So it's not only a big yoke of steel, there are many, many small shims, small parts we can use to tune the field to high uniformity.
So the Brookhaven experiment measured exactly the same thing that we're trying to measure in the Fermilab experiment. And the reason that we're doing it again is because it produced this really, really exciting result. And the reason it was so exciting is that it was quite significantly different from the standard model prediction. And nobody was expecting it, and no one really had a good explanation for why. but it wasn't enough different to call it a discovery of something new. For it to be called a discovery, the gap between the theory and the experiment has to be really, really more precisely known. So the theory community worked on reducing their error bars, and for the experiment side, we need to repeat the experiment with much higher statistics in order to reduce the error bar.
Improvements in the particle beam, experimental equipment, and methods allow researchers to make a measurement 4 times more precise than the original Brookhaven experiment. The new measurement has an extremely high level of precision, the equivalent of measuring the length of a football field with an uncertainty smaller than the width of a human hair.
It's just ridiculously precise. We're all going to be super proud that we managed to measure this precise number.
Now, after 4 years of assembling and calibrating the magnet, and more than a year of data collection and analysis, the Meon G-2 collaboration has its first result.
The unblinding was an incredible moment for the team. We finally agreed the analysis was complete, and we had to, what we call, open the envelope, where the secret decipher code is. So that number then got typed into a computer with nearly 200 people watching in a special Zoom meeting. Whoa!
Wow!
Oh my God. Yeah!
Congratulations!
Woo! Congratulations. The new result does not agree with the standard model prediction, but it does agree with the previous experiment published almost 20 years ago. You can see the standard model on the left side, and you see the new average of the experiments on the right side. And there's a big gap of white space between them. As the gap gets bigger, this is what we mean by the significance. Many people ask whether we have really discovered something, but in our field, we like to set the bar of the significance of a new result pretty high, higher than most people might say. If you think about this in terms of a football field and you're trying to score a touchdown, we're in the red zone right now. We're in the red zone. And we need a little bit more data to either push it over, but you never know if the defense is going to come along, that being the standard model, and just kick us back. So we're sort of close, but not quite there. This is outstanding confirmation of experimental technique and very, very suggestive of the possibility of new physics. That's what we're after. That's the game.
Luckily, the Fermilab Muon G-2 experiment is not over yet. The team plans to carry out a total of 5 runs of the experiment by 2022. An analysis of the complete dataset should reveal whether the wobbling of the muon represents a resounding success of the standard model, or rather, the sign of exciting new physics waiting to be explored.